Okay, next up we've got Laurent Bernard who's going to be talking to us about the evolution of kube proxy.
Hello everyone. I'm going to talk about kube proxy. So, very quickly, I work for
the mic live?
we're a monitoring company.
I can't tell if the mic is live. Please. I think your mic is not on. Is it green on the box? Oh, yeah, you should wear that, yes.
I'll do that.
No, the top, there's a slider on the top.
Yes.
Is it green? It's not green. So move that. Okay, should be good now.
Okay. Oh, that's
Much
better.
Yay.
So, as I was saying, I work at Datadog. We're a SaaS monitoring company. And I put a few figures on the slide, but what matters most is we run a pretty large infrastructure, and we run a lot of Kubernetes clusters, some of them very big, up to 3,000 nodes. And of course, as we run large clusters, we've had a few issues with Kubernetes, and some of them related to accessing services at this scale. And that's why I got very involved with kube proxy, and in particular with IPVS mode for kube proxy. So just to get started, some very quick background on kube proxy itself. So kube proxy is a component that's responsible for managing the service abstraction in Kubernetes. So it's a component that runs on every node, and it's going to enable access to cluster IP, which is a virtual IP from this node. And so basically, when you try to access a service, you try to access this virtual IP, and kube proxy is responsible for transforming this IP into a pod backend. If we look at what a deployment and a service look like, here on this example, you have a deployment of 3 pods. And what matters for this deployment is it has a label, which is the app is called echo. And then you have a matching service on the right-hand side, which is selecting pods from this deployment by using the selector saying, select all the pods with label app equal echoes. And when you create all these objects, you're going to have all this created. So first, you're going to create the deployment. The deployment is going to create a replica set, which is responsible for creating all the pods. So in our case, we have 3 pods, and the replica set is going to manage these 3 pods. So as I was saying before, all these pods have a label, and the service is matching the same label. So it's going to consider all these pods as backend for the service. There's actually an additional component, which is called an endpoint. And this component is completely managed by Kubernetes, by the control plane. You will almost never see it because you don't interact with it. And this endpoint is actually an optimization so that kube proxy and all the nodes doesn't have to watch all the pod objects, which can be pretty big. A pod object is easily 1,000 bytes, quite often bigger. And of course, if you have a large amount of pods and large amounts of service, if you need to add in memory the description of all the pods on all the nodes, it's going to be pretty big. So the endpoint object is actually a very simplified view of all the IPs backing a given service. So in my example here, you can see that the endpoint is a very simple structure with the IP of all the pods backing the service. There's an additional concept, which is called readiness. In Kubernetes, you can associate a readiness probe with a deployment. And in this case, a pod won't be ready unless it satisfies this readiness probe. And the way it works is you can, for instance, specify an HTTP probe and connect to a path and verify that it's RC. And the way it's used is basically if a pod is not ready because it can't serve traffic, it won't be added as an endpoint. So when an application tries to connect to the service, it won't be routed to that pod. So if I get back to the example I was giving before with my echo service with 3 pods, if I connect in another pod and connect to a virtual IP, the IP in 10.200 here, this is the IP of the service. I'm actually going to be connected to the pod, and as you can see on this slide, the pod is just giving as an answer their own source IP. And you can see that I'm actually getting to 3 different pods, which are the 3 pods backing the service. Of course, if one of the pods was not ready, I wouldn't be routed there. And so if of the 3 pods, only 2 were ready, I would see only 2 IPs there. So this is the very quick introduction on what kube proxy does. So how does this all work? So in order for a pod to be added to an endpoint, it needs to be ready, it needs to be running on a node, and it needs to be ready. And the component that's responsible for giving this information to the control plane is the kubelet. The kubelet is the main component running on each Kubernetes node. And the kubelet is responsible for starting pod by interacting with the container runtime and also performing the health check if there's a health check for the pod. And the kubelet will all the time give information on the pod that are running on the host and update the status. Is the pod running? Is the pod ready? All this information. And this information is going to be reported to the API server and stored in etcd, which is the data store for Kubernetes. And this is now translated to endpoint by a very specific controller in Kubernetes, which is called the endpoint controller. And the role of this controller is just to maintain the endpoint objects. So the endpoint controller is going to watch for all the services and all the pods and update the endpoint object for all the services based on all the pod matching a given label that are ready, of course. Now that we have this endpoint object that is synchronized by the endpoint controller, if we want to access a service from a node, from a container, this is where kube proxy enters into play. So kube proxy is responsible for watching services and the endpoint associated with each service, and to configure something that I call a proxyer, and you're going to see why I call it a proxyer, because you have different ways to do that. And when the client is going to connect to the service using the virtual IP, the proxyer is responsible for sending traffic to actual pods. Okay, so I'm a client, I'm trying to talk to the echo service I mentioned earlier, I'm sending traffic to the virtual IP, and the proxyer is going to route me either to pod 1 or pod 2 in my example. So there are different implementations of the proxyer. The initial implementation was a user space implementation. So you can see this as an HA proxy, for instance. So you would have a local proxy running, and all traffic would be running through it. The actual implementation looks like this. So when you have a client, it's going to be rerouted, and when it sends traffic to a service IP, the traffic is going to be rerouted to kube proxy itself. Okay. So you have an IP table rules that's going to redirect traffic to kube proxy. And the way it works is for every service in the cluster, kube proxy is locally going to find an available port, bind it, and create an IP table rule that's going to redirect traffic for the service directly to kube proxy. And then kube proxy itself is going to do the actual load balancing to pod and connect to pod 1 and pod 2 in my example. So the way it works, if you look at IP tables on the instance itself, you can see that in the pre-routing chain, there's this rule capturing everything, okay, and sending traffic to the portal's container chain. And in that chain, you have one rule for each service in the cluster. And this was actually very simple. If the destination of the traffic is the service IP, VIP on the slide, to the service port, then traffic is redirected to the IP of the node, which kube proxy is binding on a specific port that's been attributed locally by kube proxy amongst available ports. So this works fine, but as you can imagine, this is not very performant, because every time you send traffic is going to be sent from kernel LAN to user LAN to the proxy, and then back on the interface. So it's not great. Also, if you do that, there's no way to actually keep the source IP. If you're accessing the service from a container, the IP you're going to see at the destination is going to be the node IP of kube proxy itself, because of course, kube proxy is going to initiate the connection to the backends. So this is not recommended anymore. I'm pretty sure if some of you are running Kubernetes today, you're not running in that mode. It's kind of deprecated, but it's definitely not recommended anymore. And the current default implementation since Kubernetes 1.2 is IP tables, which I'm going to talk about just right now. So the first mode was user space, and the second is IP tables, and this one is the default. And once again, if you're running kube proxy, it's very likely this is the mode you're currently using. And it's the one that's used in most managed offerings. If you look at GKE or EKS, for instance, on GCP and AWS, this is the mode they use. So in iptables mode, we still use iptables for redirection, but we're not redirecting traffic to kubeproxy. We're directly using iptables to redirect traffic to backend pods. So if you can see on this example that we're sending traffic to a virtual IP, and this virtual IP is denatted to a pod IP. Okay, and when the traffic comes back, you hit the contract and you're reverse natted to the pod itself. So it looks pretty simple. When we say it that way, it's actually a bit complicated. So the design is this one. So basically same as before. kubeproxy will hook into the pre-routing chain and the output chain for local traffic. And everything will be sent to a chain called kube services. And that chain will do the same type of matching as we had before. So it will match the cluster IP and the service ports and send traffic to a chain for the service itself. So what's important here is you have a new chain for every service. Of course, if you have a lot of services, you're going to have a lot of chains, and your iptable configuration is going to be kind of a mess. In that chain, you have one rule for each backend, and this is where things start to be a bit hacky. As you can see here, kubeproxy is using the statistic iptables model to randomly send traffic to the backends. And the way it does it is, well, there's a probability for the rule to apply, and if the rule applies, you route it to a pod. As you can see, when you read it for the first time, this is not very intuitive, because instead of saying 1/3, 1/3, 1/3, which you would expect if you have 3 backends, it's actually 1/3 for the first one, because there's one chance out of 3 the rule is going to apply. But then, if the rule is not matched, you only have 2 backends, and so that way it's 50% for the second one. And finally, you have a chain for each endpoint for a service, and this chain is just responsible for doing DNAT itself, so modifying the destination IP to use the pod IP. And it's also doing something that's a bit surprising when you look at it the first time. For traffic that is sent back to the pod where it was coming from, so happen traffic, we need to use SNAT. So let's look into that, because this is a bit complicated. So imagine I'm in pod 1, and I want to access a service that's backed by pod 1, okay, and other pods. If I just do DNAT, after DNAT, the traffic is going to have the same source IP and destination IP, and of course, this will not work great. And so in that case, what iptable does is it's doing source natting to the host IP, so traffic can be reverse natted back to the destination. Another thing you can do with Kubernetes services, people tend not to use it much, and I think it's a good idea because it's a bit complicated too, is to use affinity. So what you can't want for your application is for all traffic from the same source IP to get to the same backend, because you have some sort of affinity constraints. And as you can imagine, doing persistency with iptables is not easy. So the way this is done is using the recent module, which usually people use for security to avoid port scanning or DDoS. And in that case, what happens is when you DNAT traffic to a pod IP, you also insert this source IP into a specific set, specific recent set, with the same name for the endpoint. And then the next time you hit the service chain, okay, you remember this chain where you had all the load balancing rules. In addition to the load balancing rules, at the beginning of the chain, you have these rules there that are checking if the source IP is matching against the set that exists, and if it does, traffic is directly going to be sent to the matching endpoint without going through load balancing rules. So this works, but this also feels quite, a bit hacky, and it's very difficult to expire connections and do these kind of things. So in terms of limitations, using iptables to do load balancing is kind of a surprising idea. It works surprisingly well, though, and it's been running for, most people are running Kubernetes this way. It's very hard to debug, though. Very quickly, you have tens of thousands of IP table rules. It's very hard to understand. And to be honest, the last time I was running in IP table mode on a mid-sized cluster of about 1,000 nodes, we had, I think, 50,000 IP table rules. And when you want to debug it and understand what's happening, it's pretty tricky. Worse, there's actually a huge performance impact, both on the data plane and the control plane. So here, I'm just quoting from a very interesting talk from KubeCon in Berlin 2017. And this is the impact of IP tables on routing performances. So what happens is, of course, if you have a lot of rules to traverse before getting to your endpoint, this means it's going to take some time to go through all the rules in the chains. And as you have more backends and more services, this can actually take quite some time. You can see in this extreme example here with 50,000 services that at one point it's taking like about 7 milliseconds just to get through the chain. So you want to establish a connection, and just going through the IP table chains is going to take you a few milliseconds. And the worst part is actually not the data plane, it's the control plane. Because the way kubeproxy works when used in IP table mode is every time there's a change in endpoint of services, it's going to recompute the full set of IP table rules. And as I was saying before, this can be tens of thousands of rules, and do single atomic reloads of all these rules. So it's fine on mid-sized clusters or small-sized cluster, but on large clusters, this very easily takes a few minutes. So if you look into issues on the Kubernetes GitHub, you're going to see that many people are actually getting timeout errors because by default, kubeproxy times out after 5 minutes when trying to reload rules. But it's very easy to get to go far above 5 minutes. You can see in this example that with 5,000 services, it takes more than 10 minutes. And if you reach like 20,000 services, kubeproxy becomes completely unusable. In this example here, it took them 5 hours to just reload one set of rules. As you can imagine, on large clusters, endpoints tend to move quite a lot. And so you would want things to be like updated in the matter of a few seconds. So 5 hours is definitely too long. And this gets us to IPVS. So the idea of IPVS is, well, IPVS is a load balancer built into the kernel. And so, of course, it's designed for load balancing. And the way it works is actually pretty logical. For each service, you have a virtual server in IPVS backed by real servers. And when you initiate a connection, your application is just going to send traffic to IPVS. IPVS is going to select a backend, and traffic is going to be routed to this backend. And I'm just mentioning the IPVS contract because, as you'll see later, we've had some issues with the IPVS contract. When a pod is deleted, it's removed from the real servers. So you can see here that backend X is no longer a real server for service S. And what happens in that case in the kernel is traffic to this backend is going to be dropped. So this is not ideal. And the way we actually address it with IPVS is we use the sysctl I put on the top, which is going to make sure that any new packet to the established connection is going to be to clean up the IPVS contract and trigger a reset to notify both backends. So that works pretty great, but it's still not ideal. This means we don't have any kind of graceful termination. So imagine you're currently connected to an HTTP server and downloading data. If the pod is moved to terminating state, usually what you would expect is for the communication to terminate and things to continue fine afterwards. But in this case, what kubeproxy was doing in the first IPVS implementation was just remove the real server so the connection would be abruptly cut. This wasn't an issue with IP tables because even if you remove the IP tables rules, your entry was still hitting the contract, so traffic was still flowing fine after removing the backends. So addressing this took some time, but we had an implementation of graceful termination in Kubernetes 1.12, and the way this works, if you're familiar with IPVS, is pretty logical. So what we do is when a pod is set to terminating mode, we update the weight of the real server to 0. So no new connection will be established to this backend, but established connections are still going to work. So this works a lot better. For garbage collection, it's actually easy. The way it works is we have a thread that's running every few seconds, every minute, I think. That's looking for all the backends for a given, all the connections for a given backend. And when this gets to 0, the backend is removed. That's perfectly fine because it's removed as pods go down. They send a fin, and the connection is removed. There's one small issue, which is what happens if the backend is actually crashing and you don't get a fin and the connection is not properly shut down. And in that case, you have this typical contract issue that's not specific to IPVS, which is, well, the application is not going to notice that the backend is gone until either the entry expires in the contract, or it retries sending packets until it detects that the connection is stale, which by default takes 15 minutes on most Linux installations. And if you encounter this kind of issues, what we recommend in the kubeproxy IPVS community is to lower TCP retries to actually detect that the connection is failed much earlier. IPVS connection tracking has been a bit complicated. I'm sure most of you know all the issues you can have with the contract in Linux. IPVS has its own connection tracking system. And in terms of granularity, it's much less granular than the standard contract. And you can see that the default timeout are pretty high. And the main issue we've seen with this is actually the UDP timeout, which is set by default to 5 minutes. And this was very bad, especially for DNS traffic, because as you can imagine, any DNS query would actually get an entry in the contract, and it would be kept for 5 minutes. So that's one of the reasons we decided to disable graceful termination for UDP and only do it for TCP. So for UDP, if as soon as the backend is removed, we just remove the real server. It's not perfect, but it's much better, and it solves a lot of issues. One of the things we've added very recently to the IPVS implementation is an easy way to set timeout in your configuration. And we're probably going to change the default timeout soon, but we've been very careful with doing that because we don't want to break existing installation. One of the main things we plan to do is probably to change the default UDP timeout to 30 seconds, because the largest use case by far in Kubernetes environments of UDP connections is DNS traffic. And 30-second timeout is much more than enough. Ideally, what we want is be able to set the weight to 0 when the backend pod enters terminating state, and just remove it when the pod is deleted. But the current endpoint API doesn't allow this. So very quickly, in terms of status for IPVS, it works pretty well at large scale. We've been running IPVS on very large clusters for some time, and it's been very okay for us. We didn't encounter any of the scale issues I was mentioning before. Be careful though, it's not 100% feature parity with iptables implementation, which is still the reference one. And it took us some time to tune all the IPVS parameters to make it better, but we're getting there. A few things I wanted to mention that are common challenges for kubeproxy regardless of the implementation. So the first one is the scalability of the control plane. So you remember before that the interaction of kubeproxy with the rest of the cluster is using the endpoint object. And the thing is, every time there's an update to a service, a new pod, a pod changing, becoming ready or not ready, then the full endpoint object is recomputed, and this full endpoint object is sent to all kubeproxies. So it's fine if your endpoint object is small enough, but as your endpoint starts to get big, if you have, for instance, in my example, 2,000 backends, this can lead to a lot of traffic. So in my example here, imagine you have a service with 2,000 backends. each node will receive 200 kilobytes of traffic for any given update. Okay, so that's quite a lot. And of course, the API server needs to send this information to all the nodes in the cluster, which means, well, in that example, about a gigabyte of traffic, so that's quite a lot. But worst, if you're doing a rolling update, which means you're going to update all your pods in your 2000 backend service, it means one by one, they're going to be deleted and replaced, which means at minimum, you're going to do what I was saying before, 2000 times for 2000 backends, which means you're going to send 2 terabytes of traffic, and this is, of course, quite a lot. So this has been addressed very recently in Kubernetes by using endpoint slices. So the idea is that instead of using a single endpoint object for large services, an endpoint can actually be backed by multiple slices, and the maximum size of the slice is 100 endpoints. And so you only need to synchronize the slice where an endpoint change happened, which means it's much more efficient. So this is still in beta, but this has been available since 1.17, so it's still pretty recent. Another very common issue we've seen with kubeproxy implementation is the size of the contract. All the current IPVS implementation, kubeproxy implementation rely on the contract, which means if you have services that get a lot of traffic, you create a lot of connection entry in the contract. It's especially bad for DNS. Usually in Kubernetes, you have a service that's supplying DNS to the cluster, and it's backed by pods. And of course, for each query, you then create entries in the contract. And if you run Kubernetes at large scale, what's going to happen is you're going to fill the contract and drop your DNS queries, which is not great. So there are different ways to address that. A very common way that's becoming a standard is to use a node local DNS cache on every node. Okay, so when you do queries, you would first hit the local cache, and upstream queries will use TCP. So this is much more efficient, and this is what's being used in most new setups today. Another thing is we had a very good surprise with kernel 5.0. In this example here, you can see that we have a set of container backing the DNS service, and we were very surprised that the number of entries in the contract was very different. We had like a bimodal distribution of number of entries in the contract for these nodes providing DNS, and we discovered that on 5.0 kernel, the number of entries in the contract was much lower than on 4.15. And the reason is these two commits here that optimize the way the kernel does contracting of UDP in kernel 5. And this is much better. As you can see, like the number of entries in the contract was divided by 2 thanks to these two commits. So it was very good, great news. I'm almost done. I just wanted to mention very recent features of kubeproxy. The first one is dual stack support. So Kubernetes as a whole is supporting IPv4 and IPv6 in alpha since 1.16, and of course kubeproxy is doing it too. And the most recent change and the most recent feature is the support for topology-aware routing, which will allow you to connect in preference to local pod, local meaning on the same node or in the same zone, same data center, and not load balance to all the pods. So this is still in alpha, but pretty promising. And well, in conclusion, kubeproxy is working pretty well at very significant scale. There's still a lot of effort in that place because, this talk was all about all the problems we're trying to solve with kubeproxy, but we're getting there. The main issue is IP tables and IPVS are not great match for the service abstraction because they were not designed to do client-side load balancing. They work, but they were definitely not designed to do that. So we can make them work, but it feels hacky, and we've had a lot of issues. So a very promising alternative in terms of implementation is eBPF-based load balancing. And I think some of you were there earlier to see the talk by Daniel Borkman on how they implement the service abstraction in Cilium. And this is very promising because, well, this is eBPF-based, was designed from the ground up to work with Kubernetes, and it's very efficient. And actually, in Datadog, we're actually moving to this implementation instead of kube proxy in most of our clusters. And that's it. Thank you very much.
Thank you. And we're unfortunately out of time, so questions would have to be outside the room. I'm sorry.
I'll stay around if you have questions.